de Moivres theorem. It's French. Okay, here is the basic idea. And it's an idea that we've seen already, but what de Moivres did was to bring it into one, I guess, theorem, which allows us to do things. Because you remember we said that if you raise a complex number to the power of n, then the argument just becomes n times the argument theta. And that essentially is what this is saying, because we're saying cis theta to the power of n becomes cos n theta plus I sine theta. In other words, we raise the complex number to the power of n, the argument gets multiplied by n. So sort of formalising that idea. De Moivres said for all integers n, it does actually work for other powers as well. So we can extend this idea out though, because that's nice. Remember, that's when the modulus is 1. If we just make the modulus r, we only change a little bit by then saying, because we know that the modulus will become the modulus to the power of n, and so we add that bit in there, so we can use it and say, well, r cos theta plus I sine theta to the power of n will become r to the power of n cos n theta plus I sine n theta. So if I wanted to find 1 minus I to the power of 5, yeah, sure, we could expand the whole thing out. That certainly would work. A little bit of time to do that. But we could change it to mod arg form. The modulus is root 2. The argument is minus pi on 4 for this one. So it becomes root 2 cis minus pi on 4 to the power of 5. So the root 2 will go to the power of 5, whereas the minus pi on 4 we multiply by 5. So it's 4 root 2 cis 3 pi on 4, and that's the answer in mod arg form. Notice I changed the minus 5 pi on 4. If we were to actually find the answer in the form just a plus ib, I wouldn't have to change it. Obviously, cos of minus 5 pi on 4 is the same as cos of 3 pi on 4. It's only if they were to ask the answer to be in mod arg form, then if I get an answer of minus 5 pi on 4, I would convert it so the answer is in between minus pi and pi. And so minus 5 pi on 4 is the same as 3 pi on 4. Okay. So if I do convert it back, remember I could say, oh, well, cos of 3 pi on 4, 3 pi on 4, that's in the second quadrant, isn't it? So it'll be minus 1 on root 2, and sine 3 pi on 4 will be positive 1 on root 2. So to actually work out the number there, it is minus 4 plus 4i. But we can use it to find the roots of numbers, not just square roots, which we've seen some techniques to find square roots of any number, but we can find any roots now by using fractional powers. So what we're saying is, if I know z to the power of n is x plus iy, so that's it in its normal form, if we change that to mod arg form, it becomes r cis theta, then z will become the nth root of r, and then the angle will become theta divided by n, because the nth root, remember, would be power of 1 on n. So I'm multiplying it by 1 on n, so I get theta on n. But in order to create all the possible roots, because if there's a square root I'm going to get 2 answers and so on, I need to generate all the solutions. And so that's why I add in this 2 pi k, because every revolution around the circle I'm still back at the same spot. So if I just use theta, I'd get one answer. Add 2 pi on, I'll get another answer. Add 2 pi on, I'll get another answer, and so on. It's important you add those 2 pi's on before you divide by the n, however. And so k equals 0, 1, 2, 3, however many you need to get the appropriate number of roots. In fact, you don't have to start at 0. You could start at a negative number and go negative 2, negative 1. And that can be handy if you want to create conjugates. You put in plus or minus 1, plus or minus 2, and things like that. So let's find the square root of 4i. Well, 4i is, of course, just 4 cis pi on 2. And so it'll become 2 cis, 2 pi k plus pi on 2 on 2. And k will be 0 and 1. I just want 2 consecutive ones there. So I'll get 2 cis pi on 4. That's when k is equal to 0. And 2 cis 5 pi on 4. That's when k is equal to 1. That's it in mod arg form. If I want to take it out of mod arg form, then I'd go, well, okay, cos of pi on 4, plus I sine pi on 4, and similar with 5 pi on 4. And we get our two answers there, root 2 plus root 2I, and minus root 2 minus root 2I. Yeah. How do I know? No, I just picked two consecutive numbers. Oh, right. So it's logical to start at 0 because that's a nice easy number to substitute in. 1 would be the next one. What you'll notice about these solutions is they're all nicely evenly spaced around the circle. Right? And so if you were to plot both of these points, because we're finding square roots, they would lie on a straight line going through the origin. And so I could do it this way. I could just find the first solution, which is there, and because I know they're evenly spaced, then the other one logically must be 180 degrees or pi away from that one. And so my other one would be down there, 2 cis minus 3 pi and 4. Minus 3 pi and 4, of course, is the same as 5 pi and 4. So if you remember they're all symmetric, really all you need to do is find the first one, and then you don't have to worry about the 2 pi k bit, I suppose. And you know, okay, I'm going around in an even space, however many we need. Let's find the fourth root of 16. Okay, so x to the power of 4 is 16. 16 is, of course, 16 cis 0. The fourth root of 16 is 2. That's right, isn't it? 2 times 2 times 2 times, yes. Fourth root of 16 is 2. And I've just picked 4 consecutive numbers, 0, 1, 2, 3 to use. So I've got 2 cis 0, 2 cis pi on 2, 2 cis pi, and 2 cis 3 pi on 2. And so those answers would be 2, 2i, minus 2, and minus 2i. On the diagram, the first solution was 2. I know there's got to be 4 solutions going around the circle, so there must be a solution every 90 degrees. So I'll have one up there at 2 cis pi on 2, 2 cis pi, and down there at 2 cis minus pi on 2. Ooh. Ooh, that was a bit fancy. Okay, so there's just a start on de Moivres' theorem. We'll go into a bit more detail later.